The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
That these energies, the binding energies of the electron to the nucleus, were quantized. They're quantized by these energy levels then were given by minus this Rydberg constant, R sub h, over n squared. And this n was our quantum number. It's a principal quantum number. And we saw that n, smallest value was 1, 2, ran all the way up to infinity. Okay, well, today, what we're going to do is that we're going to solve this equation, where we're going to look at the results of solving this equation for the wave function psi. Now, psi, in general here, is a function of r, theta, phi, and also time. But we're going to be looking at problems in which time doesn't have an effect. In other words, the wave functions that we're going to be looking at are what are called stationary waves. We're actually not going to be looking at the wave function as a chemical reaction is happening. We're either going to look at it before or after, but not during. And in those cases, we're looking at a wave function and the atom is just stable and it's sitting there, right? The time dependence here doesn't have a consequence. And so therefore, the wave functions that we're going to be looking at are just a function of r, theta, and phi. And we're looking at what's called time-independent quantum mechanics. Okay. Later on, actually, if you're in chemistry, a graduate course in chemistry, that's when you look at time-dependent wave functions. All right? So we're going to look at time-independent quantum mechanics, the stationary wave. Okay. Now, it turns out that when we go and solve the Schrödinger equation here for psi, what happens is that two more quantum numbers drop out of that solution to the differential equation. Remember, we said last time how quantum numbers arise. They arise from imposing boundary conditions on your differential equation, making that differential equation applicable to your actual physical problem. And so when we do that, when we do that, we get a new quantum number called L. And L is, I think you already know, angular momentum quantum number. Absolutely. Angular momentum quantum number. It's called the angular momentum quantum number because it indeed dictates how much angular momentum the electron has. Okay? It has allowed values. The allowed values of L now are 0. 0 is the smallest value of L, the lowest value of L allowed. 1, 2, all the way up to n minus 1. All right, that's the largest value it can have. Can't be any larger than n minus 1. Why can't it be larger than n minus 1? Well, it can't because the angular momentum quantum number, at least if you want to think classically for a moment, dictates how much rotational kinetic energy you have. And remember that this energy here is dependent only on n. This energy is the sum of kinetic energy plus potential energy. So if L had the same value as n, well, essentially that would mean that we'd have only rotational kinetic energy and we'd have no potential energy. But that's not right. We got potential energy. We got a potential energy of interaction. So physically, that's why L is tied to n, and it can't be larger than n minus 1. All right? All right. And then we have a third quantum number that drops out of that solution. And that third quantum number is called m. It is the magnetic quantum number, and it is called that because, indeed, it dictates how an atom moves in a magnetic field, or how it behaves in a magnetic field. But more precisely, what m is the z component of the angular momentum. All right, L is the total angular momentum. M dictates the z component of the angular momentum. And the allowed values of m are m equals 0. You can have no angular momentum in the z component, or plus 1, plus 2, plus 3, all the way up to plus L. Right. And again, m is tied to L. Can't be larger than L, because if it were larger than L, well, then you would have more angular momentum in the z component than you had total angular momentum, and that's a no-no. Okay? So m is tied to L. Right? It's the largest value you can have is L. But since this is a z component, we got some direction. And so m could also be minus 1, minus 2, minus 3, minus L. Okay? Okay. So we got 3 quantum numbers now. That kind of makes sense because we've got a 3-dimensional problem. We're going to have 3 quantum numbers to completely describe our system. All right. The consequence here of having these 3 quantum numbers is that we now have more states. So, for example, our n equal 1 state that we talked about last time. More completely, we have to describe that state by 2 other quantum numbers. So when n is equal to 1, what's the only value that L can have? 0. And if L is 0, what's the only value m can have? 0. And so more appropriately, or more completely, that n equal 1 state is the 1, 0, 0 state. And if we have an electron in that 1, 0, 0 state, we are going to describe that electron by the wave function psi 1, 0, 0. All right? Now, what I haven't told you yet is exactly how psi represents the electron. Okay? I'm just telling you right now that psi does. Exactly how it does is something I haven't told you yet, and we will do that later in the lecture today. Okay, sort of. Okay, that's the energy, right? Minus the Rydberg constant. All right, but now, if n is equal to 2, what's the smallest value that L can have? 0. And the value of m in that case? 0. And so our n equal 2 state is more completely the 2, 0, 0 state. And the wave function that describes the electron in that state is the psi 2, 0, 0 wave function. And then, of course, here's the energy of that state. Now, when n is equal to 2, what's the next larger value of L? 1. And if L is equal to 1, what is the largest value that M can be? 1. And so we've got another state here, the 2, 1, 1 state. And if you have a wave function, if you have an electron in that state, it is described by the psi 2, 1, 1 wave function. However, the energy here is also minus of the Rydberg constant. It has the same energy as the 2, 0, 0 state. Now, if n is equal to 2 and L is equal to 1, what's the next larger value of M? 0. And so we've got a 2, 1, 0 state. Again, that wave function for an electron in that state we label as psi 2, 1, 0. And then finally, when n is equal to 2, L is equal to 1, what's the final possible value of M? Minus 1. So we have a 2, 1, minus 1 state, and a wave function that is the 2, 1, minus 1 wave function. Notice that the energy of all of these four states is the same, minus 1/4 the Rydberg constant. These states are what we call degenerate. Degenerate means having the same energy. That's important. Okay. Now, this is the way we label wave functions, but we also have a different scheme for talking about wave functions, and that is we have an orbital scheme. All right? And as I said or alluded to the other day, an orbital is nothing other than a wave function. It's the solution to the Schrödinger equation. That's what an orbital is. It's actually the spatial part of the wave function. There's another part called the spin part. We'll deal with that later. But an orbital is essentially a wave function. We have a different language for describing orbitals. And the way we do this, I think you're already familiar with, but we're going to describe it by the principal quantum number and, of course, the angular momentum quantum number and the magnetic quantum number, except that we have a scheme or a code for L and M. That code uses letters instead of numbers. So, for example, if L is equal to 0 here, right, we call that an S wave function or an S orbital. So, for example, here in the orbital language, instead of psi 1, 0, 0, we call this a 1s orbital. Here's the principal quantum number. Here's S. L is equal to 0. That's just our code for L is equal to 0. This state, 2, 0, 0, you have an electron in that state. Well, we can describe that wave function by the 2s orbital. Here's the principal quantum number. Here's S, our code for L equals 0. Now, when L is equal to 1, we call that a p wave function or a p orbital. So this state right here, right, it's the 2p state because n is 2 and L is 1. This state is also the 2p wave function. And this state, it's also the 2p wave function. Okay? Now, if I had a wave function up here where L was equal to 2, we'd call that a d orbital. And if I had a wave function up here where L is 3, we'd call that an f orbital. Okay, but now all of these wave functions in the orbital language have the same designation, and that's because we haven't taken care of this yet, the M quantum number, the magnetic quantum number. And we also have an alphabet scheme for those quantum numbers. And the bottom line is that when M is equal to 0, we put a z subscript on the p. All right, so when M is equal to 0, that's our 2pz wave function. Exactly. When M is equal to 1, we're going to put an x subscript on the p wave function. And when M is equal to -1, we're going to put a y subscript on the wave function. However, I got to tell you that in the case of m is equal to 1 and m is equal to minus 1, that is not strictly correct. And the reason it isn't is because when you solve Schrödinger's equation for the 2, 1, 1 wave function and the 2, 1 minus wave function, the solutions are complex wave functions. They're not real wave functions. And so in order for us to be able to draw and think about the px and the py wave functions, what we do is we take a linear combination of the px and the py wave functions. We take a positive linear combination in the case of the px wave function. So the px wave function is really this wave function plus this wave function. And the py wave function is really this wave function minus this wave function. Then we'll get a real function, and that's easier to deal with. So that's strictly what px and py are. Px and py are these linear combinations of the actual functions that come out of the Schrödinger equation. Pz is exactly correct. Pz, m is equal to 0 in the pz wave function. All right? Now, you're not responsible for knowing that. That was just what I just wanted to let you know. So you don't have to remember that m is equal to 1 gives you the x subscript and m is minus 1 gives you the y subscript. Okay? You do have to know that when m is equal to 0, you get a z subscript there, because that's exactly right. Okay? All right, now, just one other comment here, and that is that you see we didn't put a subscript on the s wave functions. Well, that's because for an s wave function, the only choice you have for m is 0, and so we leave out that subscript. We never put a z on here or a z on there. It's always 1s or 2s or 3s. Okay? All right. Well, in order to understand that just a little more, let's draw an energy level diagram. Here's the energy again. And for n equal 1, we now see that the more complete description is 3 quantum numbers, 1, 0, 0. That gives us the 1, 0, 0 state, or sometimes we say the 1s state. Okay, there is one state at that energy. But in the case of n equal 2, we already saw that we've got 4 different states for the quantum number n equal 2. 4 different states. They all have the same energy. They are degenerate. Degenerate means having the same energy. They differ in how much angular momentum the electron has, or how much angular momentum the electron would have in the z component if it were in a magnetic field. Okay? So the total energy is the same because only n determines the energy. It's just that the amount of angular momentum, or the z component of the angular momentum, that differs in 2s, 2py, 2pz, 2px. All right? But they all have the same energy. In general, for any value of n, there are n squared degenerate states at each value of n. So, if we have n is equal to 3, then the energy is minus 1/9 the Rydberg constant. But how many states do we have at n equal 3? 9. Here they are, right? Just like for n equal 2, we have the 3s, 3py, 3pz, and 3px, and there are the associated quantum numbers for that. But now we've got some states here that I've labeled 3D states. Well, 3D, when you have a D state, that means L is equal to 2. So all of these states have principal quantum number 3 and angular momentum quantum number 2. And they differ also by the amount of angular momentum in the z direction. They differ in the quantum number m. So for example, the 3dxy has, we're going to call the m equal minus 2 state the 3dxy. We're going to put xy in the, as a subscript. For m equal minus 1, we're going to put a subscript yz. For m equals 0, we're going to put a subscript z squared. For m equal 1, dxz. And for m equal 2, x squared minus y squared. Now, again, for m equal minus 2, minus 1, 1, and 2, those wave functions, when you solve Schrödinger's equations, are complex wave functions. And what we do to talk about the wave functions is we take linear combinations of them to make them real. And so when I say m is minus 2 is the 3dxy wave function, it's not strictly correct. So therefore, again, you don't need to know m minus 2, you don't need to know that subscript, or m equal 1, you don't need to know that subscript. But for m equals 0, this is a z squared. Absolutely. All right? These wave functions are linear combinations. This one is not. It is a real function. Okay? When it comes out of the Schrödinger equation. You will talk about these wave functions, the 3D wave functions, a lot with Professor Cummins in the second half of the course. All right? You'll actually look at the shapes of those wave functions in detail. Okay, so that's the energy level diagram here. All right, all right. So now, let's actually talk about the shapes of the wave functions. And I'm going to raise this screen, I think. So what do these wave functions actually look like? Okay. Well, for a hydrogen atom, our wave function here, given by 3 quantum numbers, n, l, and m, function of r, theta, and phi, it turns out that those wave functions are factorable into a function that is only in r and a function that is only in the angles. All right? So you can write that, no approximation, this is just the way it turns out. The function that is a function only of r of r, is called the radial function. We'll call it capital R, radial function of r. It is labeled by only 2 quantum numbers, n and l. The function that is a function only of the angles, theta and phi, we're going to call y. This is the angular part of the wave function, and it is labeled by only 2 quantum numbers, but they are L and M. Sometimes we call this angular part, for short, we just call it the YLMs. Okay? So there's a radial part and there's an angular part. And the actual functional forms are what I show you here on the side screen. And in this case, what I did is to separate the radial part from the angular part. All right? So this first part here is the radial part of the wave function. And here on the right is the angular part of the wave function. And I've written them down for the 1s, the 2s, and the bottom one's the 3s, although I left the label off in order to get the whole wave function in there. Okay? I want you to notice here that the angular part, the YLM, for the 3s wave, for the s wave functions, hey, It's got no theta and phi in it. There's no angular dependence. They're spherically symmetric. All right? That's going to be different for the p wave functions. The angular part is just 1 over 4 pi to the 1/2 power. And it's the radial part here that we're actually going to take a look at right now. All right? So let's start with that 1s wave function. That 1s wave function up there, if I plotted that wave function, so this is psi 1, 0, 0, or the 1s wave function versus r. Oh, I should tell you one other thing that I didn't tell you. And that is that throughout these wave functions, you see this thing called A naught. A naught is a constant. It is called the Bohr radius. I'll explain to you where that comes from in a little bit later. But it has a value of about 0.529 angstroms. Okay, so that's just a constant. Okay, but let's plot here the 1, 0, 0 wave function. If I went and plotted it, what I'd find is simply that the wave function at r is equal to 0 here would start out at some high finite value, and there'd just be an exponential decay, right? Because if you look here at the functional form, what do you have? Well, you have all this stuff, but that's just a constant. And the only thing you have is an e to the minus r over a naught dependence, right? It's an exponential decay, e to the minus r over a naught. That's what gives you this exponential drop in the wave function. What this says is that the wave function at all values of r, right, has a positive value. Now, what about the psi 2, 0 wave function? Well, let's look at that. Psi 2, 0, 0, or the 2s wave function, is a function of r. What happens here? Well, we're plotting essentially this, right? All of this stuff is a constant. And we have a 2 minus r over a naught times an e to the minus r over 2a naught. That's what we're really plotting here. And if I did that, it would look something like this, right? So we start at some large positive value here. And you see that the wave function decreases, and it gets to a value of r where psi is equal to 0. Okay, that's a node. That's a radial node. And in the case of the 2s wave function, that radial node occurs at r equal to a naught. All right? And then the wave function becomes negative, increases, gets more and more negative, till you get to a point where it starts increasing again and then approaches 0. All right? This part here of the wave function is really dictated by the exponential term there, the e to the minus r over 2a naught. This part of the wave function is dictated by this polynomial here, 2 minus r over a naught. If you wanted to solve for that radial node, what would you do? Well, you would take that functional form and set it equal to 0 and solve for r. And so you can see that 2 minus r over a naught set equal to 0, that when r is 2a naught, that the wave function would have a value of 0. That's how you solve for the value of r at which you have a node. Now, this is really important here, and that is that at the radial node, the wave function changes sign. The amplitude of the wave function goes from positive to negative. That's important because at all nodes, for all wave functions, the wave function changes sign. And the reason the sign of the wave function is so important is in chemical bonding. But let me back up for a moment. Many of you have talked about p orbitals or seen p orbitals before. And sometimes on a lobe of a p orbital you put a plus sign and sometimes you put a negative sign. You've seen that, right? Okay, well what that is just referring to is the sign of the amplitude of the wave function. It means that in that area the wave function is, the amplitude's positive, and in the other area the amplitude's negative. And the reason the amplitudes are so important, or the sign of the amplitudes are so important, is because in a chemical reaction, when you're bringing two atoms together and your electrons that are represented by waves are overlapping, if you're bringing in two wave functions that have the same sign, well, then you're going to have constructive interference and you're going to have chemical bonding. If you bring in two atoms and the wave functions are overlapping and they have opposite signs, hey, you got destructive interference and you're not going to have any chemical bonding. All right, so that's why the sign of those wave functions is so important. Okay. So that's psi 200. What about psi 300? Well, that's the last function here on the board, or on the side walls. And let me just write down the radial part. 27 minus 18r over a naught plus 2 times r over a naught quantity squared, right, times e to the minus r over 3a naught. And now if I plotted that function, so psi 300, 3s wave function, I'd find out at r equals 0, large value of psi, finite, it drops. It crosses 0, gets negative, then gets less negative, crosses 0 again, and then drops off. In the case of the 3s wave function, we've got two radial nodes, right? We've got a radial node right in here, and we've got a radial node right in there. And if you want to know what those radial nodes are, you set the wave function equal to 0 and solve for the values of r that make that wave function 0. And if you do that, you would find this would come out to be, in terms of units of a naught, 1.9 a naught. And right here, it would be 7.1 a naught. All right? So the wave function, in the case of the 3s, has a positive value for r less than 1.9 a naught, has a negative value from 1.9 a naught to 7.1 a naught, and then a positive value again from 7.1 a naught to infinity. All right? Okay. So those are the wave functions, the functional forms, what they actually look like. Now it's time to talk about what the wave function actually means. You know, how does it represent the electron? All right? Well, this was, of course, a very puzzling question to the scientific community, right? As soon as Schrödinger wrote down his Schrödinger equation. Somehow these waves represent the particles, but exactly how do they represent where the particles are? And the answer to that question is essentially there is no answer to that question. You know, wave functions are wave functions. They're one of these concepts that you can't draw a classical analogy to, right? You want to say, well, a wave function does this, but the only way you can describe it is in terms of language that is something that you experience every day in your world, but you can't. A wave function is a wave function, right? I can't draw a correct analogy to a classical world, okay? Really, that's the case. However, it took a very smart gentleman by the name of Max Born to look at this problem. And he said, well, you know, if I take the wave function and I square it, well then, if I interpret that as a probability density, well then I can understand all the predictions made by the Schrödinger equation within that framework. All right? So in other words, he said, let me take psi, n, l, and m as a function of r, theta, and phi. Let me square it. Let me interpret that as a probability density. Probability density is not a probability. It's a density. Density is always per unit volume. So probability density is a probability per unit volume. Right? It's a probability per unit volume. Well, you know, if I use that interpretation, then I can understand all the predictions made by the Schrödinger equation. It makes sense. Okay? And you know what? That's it. Because that interpretation does agree with our observations, it is therefore, we believe, to be correct. But it is just an assumption. It is an ansatz. Right? It is an interpretation. There is no derivation for it. It's just that that interpretation works. All right? If it works, we therefore believe it to be accurate. There is no indication. There are no data that seem to contradict that interpretation. Hey, we think it's right. All right? That's what Max Born said. Now, Max Born was really something in terms of his scientific accomplishments. Not only did he recognize or have the insight to realize what psi squared was, but he's also the Born of the Born-Oppenheimer approximation, which maybe some of you have heard about before. He's also the Born in the distorted wave Born approximation, which probably none of you have heard before. All right? But, you know, despite all of those accomplishments, you know, psi squared interpretation, Born-Oppenheimer approximation, distorted wave Born approximation, despite all of those accomplishments, he is best known for being the grandfather of Olivia Newton-John. That's right. Yep. Olivia Newton-John's a singer, Greece. 2 weeks ago in the Boston Globe Parade magazine, which I actually think is a magazine that goes throughout the country in all the Sunday newspapers, there's an article on Olivia Newton-John. Long article on her, short sentence about her grandfather, Max Born. Okay? All right, so that's our interpretation. Thanks to Max Born. All right, so now, how are we going to use that? Well, first of all, let's take our psi's, our functional forms for psi here, and let's square it. And let's plot those probability densities for the individual wave functions and see what we got. All right, the way I'm going to plot the probability density is I'm going to use some dots. And the density of the dots is going to reflect the probability density. So the more dense the dots, the larger the probability density. So if I take that functional form for the 1s wave function and square it, and then plot the value of that function squared with this density dot diagram, right? Then you can see that the dots here are most dense right at the origin, and that they exponentially decay in all directions, right? So the probability density here for 1s wave function is greatest at the origin, r equals 0, and it decays exponentially in all directions. It's spherically symmetric. That's what you'd expect, because that's the wave function looks like. You square that, you get another exponential, decays exponentially in all directions. All right? So that's the probability density, probability of finding the electron per unit volume at some value r, theta, and phi. And it turns out it doesn't matter what theta and phi is, because this is spherically symmetric. How about the 2s wave function? Well, here's the 2s probability density. Again, you can see the probability density is a maximum at the origin, at the nucleus. That probability density decays uniformly in all directions. And it decays so much that at some point, you have no probability density. Why? Because that's the node. If you square 0, you still get 0. R equal 2a0. You can see that in the probability density. But then again, as you move up this way, right, probability density, as you increase r, the probability density increases again. Why? Because remember the wave function. The wave function now has changed sign. But in this area here where it's negative, if I square it, well, the probability density still is going to be large. Square a negative number, hey, you're going to have a large positive number. So that's why the probability density increases right in here. And then again, it decays towards 0. All right, so you can see the radial node not only in the wave function, but also in the probability density. All right. Here's the 3s wave function, probability density for the 3s wave function. Once again, probability density is a maximum at r equals 0. And it decays uniformly in all directions. Decays so much that at some value of r right here, the probability density is 0. Why? Because the wave function's 0. You square it, you're going to get a 0 for the probability density. And then the probability density increases again. Why? Because you're getting a more and more negative value for the wave function right in this area. Square that, well, it's going to increase. And then as you continue to increase r, well, probability density decreases. Decreases again so that you get a 0. You get a 0 because the wave function is 0 right there. This is our second radial node. But then the probability increases again, probability density increases again. It increases because the wave function increases. Square that, we're going to get a high probability density. And then it tapers off. All right? So the important point here is the interpretation of the probability density, probability per unit volume, the fact that the S wave functions are all spherically symmetric, they don't have an angular dependence to them. And what a radial node is. If you want to get a radial node, you take the wave function, set it equal to 0, solve for the value of r, that gives you a 0. Okay. Now, so far, we've talked only about the probability density in this interpretation. We haven't talked about any probabilities yet. And to do so, we're going to talk about this function here. It's called a radial probability distribution. The radial probability distribution is the probability of finding an electron in a spherical shell. That spherical shell will be some distance r away from the nucleus. So that spherical shell will have a radius r. And that spherical shell will have a thickness. And the thickness we're going to call dr. All right? So this isn't a solid sphere. This is a shell. This is a sphere, but the thickness of that sphere is very small. The thickness of it is dr. And to try to represent that a little bit better, I show you here a picture of the probability density here for the 1, 0, 0 state. And so this is kind of my density dot diagram. And then this blue thing is my spherical shell. This blue thing here has a radius r, right? And this blue thing has a thickness dr. And so I'm saying that the radial probability distribution is going to be the probability of finding the electron in this spherical shell. That spherical shell is a distance r from the nucleus and has a thickness dr. All right? Now, I want to point out that the volume of this spherical shell is just the surface area here, 4 pi r squared, times the thickness, which is dr. Not very thin, not very thick spherical shell. All right? So the radial probability distribution is probability of finding that electron in that spherical shell. It's like the probability of finding the electron a distance r to r plus dr from the nucleus. Okay? All right. Why is that important? Well, because if I want to calculate a probability, what I can do then is to take the probability density here, psi squared, for an s orbital. I can take psi squared, which is probability per unit volume, and I can then multiply it by that unit volume. In this case, it was the 4 pi r squared dr. And the result will be a probability, right? Because I have probability density, probability per unit volume times the volume. Hey, that's a probability. All right? So now we're getting somewhere in terms of figuring out what the probability is of finding the electron some distance r to r plus dr from the nucleus. In the case of the s orbitals, I said that the psi was a product of the radial part and the YLM, and the angular part. Remember that the YLM for the s orbitals was always 1 over 4 pi, the square root of 1 over 4 pi. All right? So the YLM squared is going to cancel with 4 pi, right? And you're just going to have r squared times the radial part squared. So for a 1s orbital, if you want to actually calculate the probability at some value r, you just have to take psi squared and multiply it by 4 pi r squared dr. Okay? However, in the case of all other orbitals, you can't do that because they're not spherically symmetric. And so for all other orbitals, you have to take the radial part and multiply it by r squared dr. All right? I'll explain that a little bit more next time. Okay, see you on Monday.